Lab 3 by Justin Siegel. The purpose of this lab is to determine the mass of a black hole based on the motion in orbit of a star around the black hole. In this lab, two major fundamental concepts will be used. Newton's second law of motion, which states a force is equal to the change in momentum divided by the change in time, which can be seen by the formula F net equals delta P divided by delta T, and also the concept of force of gravity, which is an attractive force from the center of a body on another body, which can be seen by the formula force equals gravity constant times mass 1 times mass 2 divided by r squared. For this lab, our system will be the star and the surroundings will be the black hole. I imported the starter code into Glowscript, first by changing the seed to my personal email. This ensures that the star has a randomized, unique trajectory as the following code shows. I then changed the mass of the star to be 2.0 times 10 to the 30 kilograms, as that was given to us, and delta T to 86,400 seconds, as that is the amount of seconds in one day. Next, I updated the initial and final position formulas, as well as the change in velocity, delta V, and the change in position, delta P. Next, I inputted code to solve for the parallel portion of FNet. I updated P hat, dmag P dt, and the magnitude of dp dt. The perpendicular portion of FNet was updated to be equal to the perpendicular portion of dp dt, and the same for the FNet parallel, as it was equaled to the parallel portion of dp dt. I then inputted a variation of the force of gravity equation so that it would solve for the mass of the black hole, or MBH. Finally, I updated the arrow scale. Using guess and check so that the arrows were visible, I found the arrow scale to be 1 times 10 to the negative 17th. Finally, I updated the rest of the arrows so that they would face the correct direction with the correct magnitude. Here is the video of the model. As you can see, as the star orbits the black hole, the direction and magnitude of the net force, or orange arrow, FNet parallel, or blue arrow, and FNet perpendicular, or purple arrow, continue to change. It can also be seen that the mass of the black hole changes slightly after each frame. In order to find the overall mass of the black hole, all of the masses were added up and divided by the number of masses so that they could find the average, which ended up being 1.39 times 10 to the 34th. Along with that, the magnitude of FNet was 9.73 times 10 to the 28th, FNet parallel 9.73 times 10 to the 28th, and FNet perpendicular was 1.1 times 10 to the 29th. Technically, the values for the parallel and perpendicular components for both the net force and the change in momentum are the same. The object's force is directly related to momentum over time, so the momentum only happens because of this force. So in all, the rate of change in momentum is due to an external force. While they may have the same value, they actually represent two different things. If the mass of the black hole was changed, but the location of the motion of the star remained the same, it would not be possible to determine the difference between the two black holes. This is due to the force of gravity equation, as seen on the slide. If none of the other variables are changed, or the star stays on the exact same trajectory, it is not possible for the mass of the black hole to be any different. If the trajectory was changed, mass of the star was changed, or the force was changed, then it would be possible to tell a difference between the two black holes. Thank you so much for listening in on my lab.